natural convection systems. Okay, so if you're a first-year chemical engineering student, this is going to be super helpful. We're going to cover the big differences between forced and natural convection. How heat can move all on its own, without any pump or fan pushing it along. All right, first up, what's the driving force here? Well, unlike forced convection, natural convection is all about changes in a fluid's density when it gets heated. It's actually pretty simple when you think about it. Hot fluid is less dense, so it rises. Colder, denser fluid sinks to take its place. This whole cycle is powered by what we call buoyancy forces, and they're basically the engine for this type of heat transfer. Second, let's talk about the unique flow pattern you get. So when you heat a surface, like a vertical plate, this special free convection boundary layer forms. And what's really interesting here is the velocity. It starts at zero, right at the wall, speeds up to a maximum inside that layer, and then slows right back down to zero. This flow starts out really smooth, that's laminar, but can get pretty chaotic and turbulent as it moves up the plate. And finally, we have the Grashof number. This is a really big deal. Think of it like the Reynolds number, but for natural convection. It's a dimensionless number that basically tells you the ratio of those buoyancy forces we talked about to the viscous forces, which is just the fluid's internal friction. It's the main thing that tells us if the flow is going to be laminar or if it's about to switch over to turbulent. So, to wrap it up, natural convection is driven by density changes and buoyancy. It creates a very specific velocity profile in its boundary layer, and the Grashof number is what tells us how it's all going to behave. Let's dive into more detail.
Have you ever stood in a room and wondered how a simple hot radiator can warm the whole space up? I mean, there's no fan, nothing's pushing the air around. It almost feels like magic, but it's actually this really beautiful piece of physics at work. So today, we are going to dive into the science behind this everyday wonder, natural convection. It's the invisible engine that drives heat, all on its own.
All right, so here's our game plan. First, we'll figure out what this invisible engine really is. Then, we're going to zoom way in on something called the boundary layer. That's where all the action happens. After that, we'll get into the fun stuff and build the equation of motion from the ground up, which will lead us to the big reveal of the Grashof number. Finally, we'll put it all together to solve the mystery and see how this theory lines up with what we see in the real world.
So, let's kick things off with that big question. What is this invisible force that moves heat around so effectively when there's no fan in sight? Seriously, think about it for a second. There's no pump, no fan, no obvious external force. The air just moves. But it isn't magic, of course. It's all driven by something really fundamental that's happening to the air itself. And that something is called natural convection, or sometimes free convection. And here's the core idea, and it's pretty simple. When you heat up a fluid, like the air around a radiator, it expands. And when it expands, it gets less dense. So what happens? Well, the cooler, denser air around it is heavier, and gravity pulls it down, effectively pushing that warmer, lighter air upwards. That upward push is what we call a buoyancy force, and that's it. That's our invisible engine. It creates this continuous, rolling current that carries heat all through the room. Okay, so to really get this, we need to zoom in. We've got to look at the exact place where this engine gets started, which is this super thin layer of fluid right up against the hot surface. Now, in engineering and physics, whenever we tackle a complex problem, we always start with the simplest case we can possibly model. For natural convection, the absolute classic problem is a heated vertical flat plate just sitting there in a still fluid. It's like our perfect little laboratory for this whole investigation. So the second that plate gets hotter than the fluid around it, this boundary layer starts to form. It's just this thin little region of fluid right next to the plate where everything happens. The fluid in this layer gets heated, its density drops, and it starts to creep upwards along the plate. Now this is where it gets really, really interesting. Take a look at the velocity profile inside that boundary layer. It looks totally different from what you'd see if you were, say, blowing air with a fan. Right at the surface of the plate, the velocity is zero. That's the no-slip condition you always have. But then, as you move away from the plate, the velocity actually goes up, hits a maximum, and then it goes all the way back down to zero again at the edge of the boundary layer. That peak is a huge clue. It tells us that the force making the fluid move is being generated inside the fluid itself. So how on earth do we describe this with math? Well, we need to build an equation of motion that can capture all of these forces that are at play. You can think of it like we're detectives, assembling clues to solve a physics mystery. We're going to start with the absolute foundation of fluid dynamics, a momentum balance. This is basically just Newton's second law, F equals ma, but for a tiny little cube of fluid.
So, the change in that fluid's momentum has to be equal to the sum of all the forces acting on it. That means pressure forces, viscous forces, which is just friction, and the really important one for us, gravity.
And right here is where it all clicks into place. This entire process is driven by the tiny, tiny difference between the fluid inside that boundary layer and the fluid way out in the rest of the room. Inside the layer, the fluid is hotter, so it has a lower density. We'll call that rho. Outside the layer, the fluid is cooler, so it has a slightly higher density, which we'll call rho infinity. That small difference in density, once gravity gets a hold of it, creates our engine. This term, right here, G times the quantity rho infinity minus rho, that is the net buoyancy force per unit volume. Gravity is pulling just a little bit harder on that denser fluid outside, which in turn shoves the less dense fluid inside upwards. This one term is what makes the whole magic of natural convection happen.
Now, trying to measure density changes directly can be kind of a pain, so we use this super handy fluid property called the volume coefficient of expansion, or beta. Think of beta as our translator. It tells us exactly how much a fluid's density will change for every degree of temperature change. It's what lets us rewrite that tricky density term as something we can measure easily: temperature.
And this brings us to a really critical point. Once we make that substitution, our final equation of motion shows that the fluid velocities, u and v, are now directly tied to the temperature difference T minus T infinity. This is huge. It means the momentum equation and the energy equation are coupled. You literally cannot solve for the velocity if you don't know the temperature, and you can't figure out the temperature profile if you don't know the velocity. They are completely locked together. Okay, so we have this complicated coupled equation. How do we make it practical? How do we get an answer out of it? What we need is a way to sort of package all this complicated physics into one single powerful concept. So the real question becomes, how can we compare the force that's creating the motion, that's buoyancy, to the force that's resisting the motion, that's viscosity, or the fluid's friction? If we can answer that, we can predict what the fluid is going to do in pretty much any situation. And the answer is a new dimensionless number called the Grashof number. If you've ever dealt with the Reynolds number in forced flow, the Grashof number is its natural convection twin. It is literally just the ratio of the buoyancy forces to the viscous forces. It tells us, point blank, which force is winning the tug of war.
Let's really break this equation down, because every single piece tells an important part of the story. Up top, in the numerator, you've got all the forces that are driving the flow. There's G, gravity. Without it, the engine doesn't start. Then there's beta, our expansion coefficient, multiplied by the temperature difference between the wall and the fluid. That whole chunk together is the source of our buoyancy. A bigger temperature difference gives you a stronger upward push. Then we have x cubed, which is a length term. Buoyancy acts on the whole volume of the fluid, so that gives it scale. Now down in the denominator, you have the forces trying to stop the flow. That's nu squared, or the kinematic viscosity squared. You can just think of viscosity as the fluid's internal stickiness. So the Grashof number is really just a powerful ratio. It's the strength of the buoyant push versus the fluid's own resistance to being moved.
All right, now we have the Grashof number. This is the key we've been looking for. We can finally unlock the solution to our original problem, which was all about calculating the rate of heat transfer. Let's not forget what we're really after. It's not just about watching fluid move. We want to know how much heat is actually being transferred from that hot plate. And we measure that with the heat transfer coefficient, H, which we then package into another famous dimensionless number, the Nusselt number. The Nusselt number basically tells us how much better convection is at moving heat compared to if the fluid just sat there and let heat conduct through it. And here it is, the grand finale. All of that incredibly complex physics boils down to this one beautiful relationship. This equation shows us that the Nusselt number, our answer for heat transfer, is a function of two key dimensional groups: the Grashof number, which tells us about the fluid motion, and the Prandtl number, which is all about the fluid's thermal properties. This is the solution. By calculating Grashof and Prandtl, we can directly predict the heat transfer rate. It's an amazing connection between the cause, the buoyancy-driven flow, and the effect that we actually care about, heating up the room.
Okay, so this is all great. The theory is elegant, the math works out, but does it actually match what happens in the real world? Let's find out.
Wow. So this is not a computer simulation. This is a real photograph. It was taken with a special device called an interferometer, which lets us actually see lines of constant temperature, what we call isotherms. And you can see it so clearly, the boundary layer forming along that vertical plate. See how the lines are packed really close together near the surface? That shows a really steep temperature gradient, which is exactly where the most heat transfer is happening. This picture is just a stunning physical proof that the mathematical model we just spent all this time building actually describes reality perfectly. We made the invisible visible. So, we've cracked the case for nice, smooth, laminar, natural convection. But what happens when we turn up the power on that invisible engine? What if the temperature difference gets really big, or the plate is really, really tall? The Grashof number gets huge, and just like what happens with the Reynolds number, the flow eventually stops being smooth and becomes chaotic and turbulent. And well, that's a whole other fascinating story.